All right, everyone, we've got an action-packed hour, so I'm going to go ahead and get started so we can stay on time. I want to welcome everyone to the AAVSO webinar series. My name is Whitney Armentar, and I am the Development Director for the AAVSO. It is great to see all of you here. Today, we're going to hear a great presentation from Dr. Karen Collins on the TESS Follow-Up Observing Program. But before we dive in, I have a few little bits of housekeeping. So first, a quick tour of Zoom webinar. If you take a look at the bottom of your Zoom window, you will see a few buttons. There's the chat box where we've all been introducing ourselves and saying where we're from, and please feel free to keep doing that. There's a CC or show captions button, which allows you to enable or disable Zoom's automatic closed captioning. And there's also a special button labeled Q&A. If you click on that Q&A button, you will have the option to submit questions for our instructors for Dr. Collins today. You can submit as many questions as you like at any point during the presentation. Don't worry, you're not going to interrupt anyone. After the presentation, we'll have an extended Q&A where we'll try to answer as many of your questions as possible. Please make sure that you use the Q&A box when you're doing this. We will not be taking questions from the chat. We will only be taking them from the Q&A box. I'd also like to take a moment right now to express our gratitude to our 2025 series sponsor. Boise Astro provides online astronomy education, observatory resources, and research experiences to students and schools to perform observations, conduct research, and publish results. Please check out their website at boiseastro.org to learn more about their offerings in astronomy and photometry. Support from sponsors like Boise Astro and our donors make the work of the AAVSO possible. To support the AAVSO, please consider a donation by scanning the QR code on your screen or going to aavso.org. All donations are tax deductible and support our mission of enabling anyone anywhere to participate in scientific discovery through variable star astronomy now and for generations to come. So with no further ado, it is my pleasure to introduce Dr. Collins. Dr. Karen Collins is a member of the Transiting Exoplanet Survey Satellite, TESS, Science Office. Her roles include leading the TESS Follow-Up Observing Program, Time Series, Photometry Subgroup, and analysis of TESS light curves as part of the TESS Objects of Interest team to produce quality planet candidates for follow-up confirmation and characterization. Dr. Collins is also a co-PI of the LCOGT KEEP project aimed at TESS follow-up observations and is the lead developer of AstroImage, a graphical user interface-based astronomical image data reduction and precision photometry open source software package. She obtained her PhD in physics and astronomy at the University of Louisville, and astronomy is a second career for Dr. Collins following an engineering career in the telecommunications industry. She holds an MSEE and BSEE from the Georgia Institute of Technology. And with that, I am very happy to turn this over to Dr. Collins.
Hello, everyone, and thank you. I've noticed a worldwide audience here. I would say thank you for spending a part of your Saturday afternoon to learn more about TFOP, but it's probably not afternoon for a lot of the people I saw coming through. I am going to tell you about the TESS Follow-Up Observing Program, and hopefully could be an opportunity for some of you to contribute to TESS exoplanet discoveries if you're not already doing that. I've seen some TFOP members already popping through. Start with the really basics. What is an exoplanet? Basically a planet just like our own solar system that orbits a star outside our solar system. In other words, a star that's not our sun. We know of nearly 6,000 exoplanets to date, and they range from Earth-like all the way up to gas giants. We want to find as many exoplanets as we can for many reasons. We study them to understand planet formation, evolution, demographics, atmospheres of the planets, and the possibility of habitability on those planets. In addition, the TESS spacecraft and its technique also uncovers a lot of brown dwarfs and low mass stellar companions to our target stars. And those are also interesting to a lot of scientists. So we do follow up these type systems as well sometimes. Let's talk about a couple of the key transit detection, exoplanet detection techniques. First, we'll talk about the transit method. And basically, it's when the planet passes or transits in front of its host star from our perspective here on Earth, causing a small dip in the star's light curve or brightness. The depth can give us the size of the planet, and that size is relative to the host star, but we have ways of determining the size of the star. Then from repeating transits, we can obtain the orbital period as long as we can rule out transits between any two transits. So let's talk about another key method called the radial velocity method. This is key because it gives us a mass measurement, whereas transits give us a radius measurement of the planet. So they're very complementary methods and work together to give us the most data well, not the most data, but a lot of data about the planet. So the technique measures the star's wobble as it has a very small orbit itself induced by the gravity of the planet orbiting the star. And that wobble appears as a Doppler shift in the star spectrum. And we can create these measurements of the amount of shift and plot it out. And we can learn about the orbit of the star. And this is what reveals the mass of the planet. We have instruments that are precise enough now that we can detect these velocity changes as the spectrum moves back and forth as the planet orbits the star. We measure these small shifts down to a meter per second now, which is what we need to work with Earth-type planets. Now we can combine, if we have transit data and radial velocity data, we now have the planet's size or radius, and we have its mass. So we can determine the bulk composition or the bulk density, and then we can derive constraints on its composition using models, interior planetary models. Let's talk about how we got to 6,000 transiting planets so far, and some of the surveys that have helped do that. They have been from the ground and from space. Some of the key ones from the ground are HatNet, WASP, KELT. KELT is the survey that I grew up on. It's where I did a lot of my graduate research. And NGTS is still operating. They basically use networks of small to medium-sized telescopes, and they monitor a very wide field of view, millions of stars, and look for little dips in those stars. But they're only sensitive generally to gas giant planets that are close into the star, or hot Jupiters. NGTS can probably do a little better than that. They have larger telescopes. Then we had the space-based transit surveys that I'm sure you all know, Corot, Kepler, and well, K2, the extended or refurbished Kepler mission, and now TESS. And TESS is our topic of the day. But these satellites are above the atmosphere, of course, so we can achieve higher photometric precision because we don't have to deal with weather, and for the most part, we don't have to deal with day-night cycles. So we can just observe for extended periods of time. Because of that, we can detect smaller planets on longer period orbits. And with this broader range of types of planets that we can now discover, we can do statistical studies of exoplanet populations. Okay, so let's focus in on the TESS mission now. It launched in 2018, and since then it's done nearly an all-sky survey to find planets around the brightest and most nearby stars. It will be starting its 8th year of operation, third extended mission in less than a month. The observing strategy of TESS is pretty unique. It has 4 separate cameras, you can see in the upper right here, and they are aligned so that their fields of view are on top of each other, along the oriented along the ecliptic. And the fields, then the overall field gives you 24 degrees by 96 degrees. And then, as you can see, the telescope repoints approximately every month. And over the course of the year, we get 13 sectors, which generally cover one hemisphere or the other. There are times when we take a break and do some ecliptic plane observing as well. The strategy also, if you'll notice, every one of the sectors has a region that gives continuous coverage, this circular area here. There's one in the southern ecliptic plane, a southern ecliptic hemisphere, and in the north. They're indicated by the orange here that shows up. So test results so far. We have over 7,500 planet candidates from TESS. We refer to these as TESS Objects of Interest, or TOIs. 687 published TESS planet discoveries as of a couple of days ago, maybe more by today. 373 planets that are smaller than Neptune, and 80 planets that are smaller than 1.5 Earth radii. And 500 of these planets have mass measurements. And a lot of our planets are prime targets for JWST atmospheric observations. So let's talk about the TESS image pixel size. It's one little bit of a complication in that the pixels are quite large on the sky. Each pixel covers 21 arc seconds by 21 arc seconds on the sky. So we have photometric apertures, which I've represented here with the red outline, that are roughly 60 arc seconds by 60 arc seconds. That's very rough. But they're, depending on the pipeline, they can be irregularly shaped, like this one, and that's what the Spock pipeline uses. QLP is a different pipeline. It uses circular apertures like we use for ground-based photometry. But the point is, you will notice that there are almost always several stars inside the photometric aperture. So TESS knows that there's a dip in flux coming from inside this region. It just doesn't know exactly which star that the dip in flux is occurring in. So this gives us a need for ground-based follow-up. Again, we just know we have a dip in the flux inside this region, but we need to figure out which star it is. And we can use our ground-based telescopes, even our modest citizen scientist telescopes. Your pixel size is probably usually an arc second or less. And your photometric apertures can usually be 3 to 5 arc seconds, depending on your seeing. So you can do much better spatial resolution observing than TESS can do. But even within a smaller ground-based light curve photometric aperture, seeing limits us from the resolution that we can get. So there are techniques to do imaging that's better than seeing limited such as adaptive optics and speckle imaging. And these techniques can reveal companions to the target star. Here's an example of the target star in the middle, and you'll see there's another blip in the light over here, which is about 0.3 arc seconds away from the target star. It shows up above and below, but that's just an artifact of this technique. It's only one star. So this can reveal companions. A downside of this is usually photometric precision. If you're trying to do time series, adaptive optics or speckle, you can't get the good enough photometric precision to do light curve work for planetary transits. So they can tell us we know there's another star there, but we still don't know for sure which star hosts the event. We have another technique with spectroscopy that can reveal even closer in stars, referred to as spectroscopic binaries. And the way we know that these stars are there is we'll expect a single line in the spectrum in a particular place, and it'll be split into two lines like you see here in the black curve in the background. And that splitting is because the stars are at different velocities moving toward or away from Earth. And that's typically attributed to the orbit of two stars around each other. The stellar spectroscopy can also let us know that a star is rotating too fast for us to do precise radial velocity measurements. And we'll talk more about what those are in a bit. But you need nice sharp lines to be able to accurately measure where the center of that line is. And when a star is rotating rapidly, it spreads that line out in a very broad way. So you can't get as fine a measurement of the center of that line. So a lot of times we'll set those type stars to the side and say that's for the future or some other technique to try to confirm that that system is a planet or a false positive. So we also need to measure the mass of the planet where practical. Currently, we need fairly bright stars to do that. So TESS is a good match for this technique because it's studying bright stars. It's observing bright stars. That's what it was designed to do. And the mass that gets measured may reveal a planet, such as this case here. You'll notice the axis over here is in meters per second. So this is a very small signal, and that corresponds to a planet. You need to know the mass of the star, but that tells you the mass of the planet. Then instead, you may find a binary. In this case, notice the units are kilometers per second. So this is a huge swing in the radial velocity variation that shows that there are two stars orbiting each other. The final thing that we can get from radial velocity measurements is the eccentricity of the orbit. You'll notice that this shape here is very different from this shape. And what's going on is this is approximately a circular orbit for the radial velocity variations, while this is an eccentric orbit. Okay, so how do we organize this work by all the people around the world that want to work together to confirm TESS planets and get them published? Since the start of the TESS mission, the TESS project and NASA have supported the TESS Follow-up Observing Program, or TFOP for short. It's led out of the Smithsonian Astrophysical Observatory, part of the CFA. And the goal is to foster communication between all the people and coordinate the systems that they want to work on. So if we can get folks to spread out, we have so many planet candidates. If we can get folks to spread out instead of working on the same planets, we can get more science output, and we can reduce the duplication of effort that people may otherwise be doing if they're not aware of what other teams are working on. We're organized into 5 subgroups. The first subgroup is called ground-based light curve photometry, and we refer to it as subgroup 1 or SG1. You'll hear a lot. I lead that group, and I think this is the group that is most applicable to work by that can be contributed by AAVSO members. There are also recon spectroscopy that's led by Sam Quinn, my colleague. High resolution imaging led by David Giardi at Caltech. The precise radial velocity group led by my boss, David Latham. He also leads the overall TFOP team. And then finally, there is a space-based photometry group led by Diana Dragomir, and it originally organized Spitzer observations, but it was decommissioned not too long after TESS started science operations. So now it's primarily KOPS and NEOSAT. NEOSAT's a smaller Canadian satellite, but it's good for doing photometry of transits. We currently have over 700 members, and 500 of those are registered as SG1 members to do light curve work. And of those people, we have 280 observatories registered. The way that we organize is through the TFOP charter and through the TFOP working group publication policy. This is how we organize together fairly. We respect each other's work. There are guidelines provided in the documents, and everybody agrees to work by those documents. So if you contribute observations to SG1, you will generally, if they are useful for a publication, you will generally be credited for that with the offer of co-authorship on that publication. The results that we get are all hosted on a tool that's called ExoFOP, and that is provided by Nexi at Caltech. It's not, that's one of the tools I'll talk about, a lot of tools that the SG1 team provides, but that one is done out of Caltech. So let's dive deeper into the SG1 overview. Again, we do the ground-based light curve photometry, and our goals are primarily to determine the true source of the TESS dip, the detection of the dip in the TESS light curve. You can see an example here where TESS just measured a dip in its overall light curve that included 2 stars, actually more than 2, but I've zoomed in on them here. But our ground-based light curve separated the stars and showed that the fainter star is the one that has a very deep eclipse, and that the target star itself is flat. So we call these nearby eclipsing binaries, and then we retire these as what we call a false positive. And we flag in our notes that, well, this is not really a planet candidate. It's instead a nearby eclipsing binary. We also, as we're collecting our observations, some of the TESS ephemerides can be uncertain, such as this case at the bottom right. This event occurred about an hour early. So we will take this information and we will revise our ephemeris for our future follow-up. And we can also revise the depth if we find differences and the transit duration. We also check for color dependence across the optical and IR bands. Since TESS is a single band photometer, it can't do the different color measurements, but we can do that from the ground with our filter sets. And you can see at the bottom in B band, this system is flat in B band, but there's a significant dip in the ZS band, which is in the IR. So we call these probable false positives. There are configurations where this can happen if you have a background star. So we don't completely throw them away, but there are likely false positives. We also conduct long-term TTV observations, and I'll talk about why we do that in a bit. And we try to track down some orbital ephemerides are, plus or minus 1 hour is okay. We can kind of manage that from the ground easily with a single observation. But some ephemerides can be uncertain by over a day, and that gets tougher to do from the ground. But we have organized campaigns where we do try to pin some of these down so that they can be studied further by expensive telescope observations such as from JWST. Finally, we try to determine the true orbital period of TESS duo transits. And I've got a slide here on what a duo transit is. So in this case, this is a light curve of the TESS data down here at the bottom. So you will notice there are some black data points that you can hopefully see here on the left. And there is a faint dip right above this blue triangle. That is a transit. This is 2 sectors of TESS data. Each one of these red vertical lines is a TESS sector. So this is about 54 days of coverage. But 2 years later, because of how TESS observes, we get another 27 days of coverage, one more sector. We see yet another transit happening here. Then finally, 2 years later, or 4 years after the initial observation, we get one more sector, but there are no transits in those data. So we have 2 transits, and that means that because of this large data gap, these 2 transits are consistent with a family of orbital periods. It's not just the orbital period here, because another transit could occur right in the middle here, or 2 transits could occur, or 3 more transits could occur. So the upper orbital period is limited by the 2 transits that we do detect, but the lower orbital period can continue to decrease until we get down to the point where we would start to see another transit in these 2 contiguous sets of observations. So we can set kind of a 54-day lower limit on the orbital period. Those can be parameterized, the set of periods, as the maximum period divided by integers, starting with 1, which will give you the maximum period, 2, 3, 4, 5, all the way down until we get to a period that's just above the 54 days for this particular data set. Our ephemeris prediction tool that you would use to find transits to observe on any particular night from your observatory, it handles this for you, and it will present opportunities to observe these different periods. As I mentioned, we've got 500 members and over 280 observatories. They're not all shown here. It gets a little crowded. But the key point I want to make here is that we have professional astronomers working together with student astronomers and citizen astronomers, all from the same tool set. So everyone's data can complement the other data. We also get some ground-based surveys that provide mostly historical data. Some in NGTS is still operating. They also actually do some test follow-up as well. Okay, let's talk about a quick overview of the software tools that we provide and web tools that we provide. And then I'll dive a little deeper into each one. We have a TESS transit finder, which is the tool you'll use to select a transit to observe on any particular night from your observatory. And this version is private to TFOP members. And there's a reason it's private. I'll talk about that on the next slide. The next tool is the TOI SG1 TOI list, and it's a shared Google spreadsheet. This is the database basically that the TESS Transit Finder predicts transits from and produces its output, which I will show you. We have a TESS observations coordinator where you can post observations that you're intending to conduct. A field of view tool to help you plan observations and reduce data. A Gaia apertures tool that helps in reducing the data. And TFOP is not a tool that's provided by the TFOP team. Again, it's from Nexi at Caltech. But it's where we put all of our reduced data products so that we can share amongst the TFOP team. And then there's AstroImageJ for data reduction. You're not required to use AstroImageJ, but I will tell you about it. And therefore, if you prefer to use a different tool, you'll know the capabilities that you will need. Okay, so this is what the TESS Transit Finder interface looks like if you go to it in the user interface mode. So you'll basically select your observatory location. If you join TFOP, your observatory would be loaded in here. And once you select it, it will always remember it and stay there. You tell it which day you want to start your transit search on. Usually you can just leave it on today. How many days in the future and in the past you want to search. And then there's, this is the basic constraints. There's a whole host of other constraints down below here that I'm not showing that you don't have to use, but they're available if you want to refine your transit search. We have a second mode too. This can be operated in a scripted mode that some professionals use when they're trying to automate their observations. This is an example of a row that you would see in the output of the TESS Transit Finder. This is one particular observable transit. You can see the portion of the transit that's observable marked in blue. And I see hands up. Do we want to break and answer questions as we're going along, or do you want me to finish?
I would go ahead and finish, Dr. Collins. Hey, everybody, if you have questions, just a reminder, please go ahead and drop those in the chat. We're not going to be doing raised hands or anything like that. We're going to be going ahead and putting those questions into the chat, please.
Okay, thank you. Yeah, so the key point here, and this is why it's private, there is a version of this that's public called the Swarthmore Transit Finder. And that's because Eric Jensen at Swarthmore develops and maintains both our private version and the public version. The public version hosts all the planet candidates that are published by MIT as they are published. Our list contains updates to the ephemerides that we get from our follow-up data, as well as when we get new test data. Greg Surdock, our volunteer, updates our ephemerides every time we get new test data for a TOI. We also update the dispositions. When we don't need any more observations, we will turn them off. and also the priority for each TOI to be observed. The key part, though, is that we provide feedback to the observers. And this feedback includes the status of the TOI. That's this entire first line. I don't want to go through all the details. There's too much for today. But it tells you everything you need to know about the TOI and why you may or may not want to spend your telescope time on it. It provides a list of the observation history, this narrative below for this transit. We have 2 observations, but the next one we need, it tells you this is what we want to observe next. We want no more observations except a transit observation in a blue filter, because now we just want to check the chromaticity to see if there's a depth difference depending on the band. And if you can't observe in a blue band with your instrumentation, then you should choose a different system. If we get too many transits in, the lead authors of papers will start refusing to include our data. So we try to limit the amount of observations that we get to be just what we need. But that information doesn't show up on the public version, only on the TFOP private version. We have a new feature coming soon to handle the high ephemeris uncertainty systems. One thing about most, I think probably all ephemeris prediction tools, is they require that the nominal ingress or egress time be included in your observation window. So if you look at this little graphic on the bottom right, the nominal transit, the center of when TESS thinks it will occur, is actually over here. But the observable window by this telescope is the dark blue line at the top. However, the uncertainty is so large that you might be able to capture a full transit that's just 1 sigma earlier than what TESS thinks. So a new version being worked on by Eric Jensen right now will provide this capability, and hopefully we'll have this out in the next couple of months. Okay, as I mentioned, the SG1 TOI list is the database, the shared Google Sheet that the TTF uses. Our members can also look at it if you want to look up information directly without going through the TTF. But this is where all the data is pulled from to produce the TTF output. I maintain this currently, and we have a couple of trained volunteers, including Greg Surdock, that does the ephemeris updates when new test data comes in. So let's look at just the overall flow of how the TFOP SG1 process works. So we get public TOIs from MIT, from the TOI vetting team at MIT, and we get custom observation requests from other TFOP members. We merge those and add them to the SG1 TOI list. The TESS Transit Finder reads from the TOI list. You will go to the TESS Transit Finder and enter your information. It will give you a list of transits to observe. You pick one and observe it. So all the things in blue are what the observers will do. Then once you're finished observing, reduce your data and submit it to ExoFOP TESS, and a summary that we will tell you what we need would be submitted to our special TFOP SG1 Gmail address. When that is submitted, it'll trigger me to go review your result. I will then interpret it and update the TOI dispositions on the SG1 sheet like these. There are a bunch of codes. They're all defined on the SG1 sheet. Way too much to go into today. And that might also include turning off a TOI, setting it to priority 4 if we need no more observations. So you should only observe priorities 1, 2, and 3, basically. So finally, I update what observation it is that we need next at the end of the comments block on the TTF. So you will know if you can do the observation that we're looking for, and then the process starts over until I do disable a TOI when we get all the observations that we need. The other tool used for planning observations is called the TESS Observations Coordinator, or TOC for short. It is basically this panel that when you click a link on the TTF for the target that you're planning to observe, this will pop up. Everything is generally pre-populated, and you may have to set your filter. But other than that, that's all you'll need to do and save it. Then your plan to observe will actually show up back in the TTF searches that other people are doing, or that if you run it again, you will see. For an event that is already being planned to be observed by someone else, it will show up as a yellow background in the priority column, this column here. So this one does not have an observer going after it, whereas this one does. If you mouse over that cell, then it will tell you who is planning to observe it. It doesn't mean you should not observe it. It just means if you think, well, maybe they're going to get data, so I'm going to go look at another one. I've got 10 other options, so maybe I'll go observe another one. But it's never bad to get 2 observations of the same event either, because you never know when weather is going to move in one place or the other. But this can avoid duplication of effort. Another tool that's handy for planning your observations and doing the data reduction is the field of view tool. Again, this was created by Eric Jensen at Swarthmore for us, and it shows the field of view that you are observing. It is zoomable and panable when you go live. I'll show you a quick example. It identifies the target star with a blue symbol. The green symbols, you can barely see them here zoomed out, but zoomed in, you can see them better. These are the stars that are bright enough in the Gaia catalog that they could be the source of the TESS detected signal. So we need to look at all of those. Unless we already know the event is on the target star, we need to examine those and make sure that the signal is not coming from one of those fainter stars. You can set the field of view of your telescope is represented by this magenta square. You can set your field dimensions here and rotation if you need to. That way you can plan your observations more easily to see which comparison stars you'll have access depending on your pointing. You can click on one of these symbols and it'll show you more information on the star. And I will just quickly show you this field live. So you can zoom in and out, you can pan if you don't like the current setup of the field. And let's just say you want to get that very bright star up here out of your field of view for some reason. You can do that, and then you can copy the center of the field by clicking this button here, and then paste that ARIANDEC coordinate somewhere else so that you can center your telescope there. Then we have a Gaia Apertures tool. This is the user interface for that. If you go to it directly, this tool provides a list of star locations that should be checked for NEBs. unless that's already been done. The notes will say in the comments column, they'll say whether you need to do an NEB check or not. But if you click on the link to that in the TTF output, it'll totally bypass this field because it knows all the information you need to enter, and it will just provide you the file download, and then you can just drag and drop that file into AstroImageJ, and then you already have your aperture set up where they need to go to do your photometry for the NEB check. I mentioned ExoFOP, our data repository. And this is provides us a list. Anyone can look on this, even non-TFOP members. They can see which observations we've already done. However, the files show up in a different section down below, and we can upload those with an optional 1 year of proprietary period. So only TFOP members can see them for the first year. The uploading can be done with a user interface that ExoFOP provides, or it can be done with a Python script that we can provide. I'm going to skip showing you those for time. Now let's go through some of the AIJ capabilities. The general overview here is that it is just an astronomical image and data analysis tool. It just can do general analysis. It provides image calibration, in other words, bias, dark subtraction, and flat fielding, a differential aperture photometry tool, light curve plotting, light curve detrending and fitting, automatic comparison star selections, various aperture options, different shapes and modes. And there is an automated NEB check written by the AAVSO's very own Dennis Conte. Thank you, Dennis. And automatic optimization of comparison stars and also of detrend parameters that you can optionally use. There is a plate solving capability that interacts with the astrometry.net servers, or for Microsoft Windows that can be installed locally. We even have a moving object tracking capability now. That's not needed for transit work, but a lot of folks trying to do asteroid work and so forth have been asking for that for a long time. Can do image alignment if needed. It's not necessarily required for transit observing, and can now also do TESS image analysis. So you can go to TESS cut, which can cut out a small section of TESS data to make it not such a huge file. You just cut out the section that you want, and you can produce light curves from that. And you can also load up spotlight curves and analyze those as well. AIJ is controlled by what we call a toolbar, the sort of the master control. It provides access to all the major astronomy tool the tools that are provided. The underlying ImageJ tools are also there. AstroImageJ sits on top of a package that was developed out of the biological sciences, but basically for microscope users. But we've added all of the features that you need to do astronomical work. And we tag on AstroImageJ, both are open source packages. We have the data processor that does the data calibration, multi-aperture, which provides the differential photometry capability, multi-plot and light curve fitting can be accessed here. Most of these items will pop up on their own when you are running an analysis, so you don't necessarily need to click these, but they're always there if you need to open them directly. And finally, a coordinate converter that does time format and coordinate format conversion. This is what the data processor screen looks like. It lets you create master calibration files, uh, do bias subtraction, dark subtraction, flat fielding, update fits headers if you need to add new information such as BJD TDB. We need timing, we need the timestamps reported in that format. And a lot of observatory control systems don't provide that format. So you can convert using data processor. You can also trigger a plate solve if you want. Then, of course, save your calibrated files. We now support FPAC to save space on your hard drive. And you can optionally run photometry and plotting. And one reason that's particularly important is you can use data processor in what I call real-time mode. So you can use it, you can set this up and use it while you're actually observing, and it will look for images to come in off of your telescope, and it will build up the light curve and plot it as your data are coming in. So you can sort of keep an eye on the quality of your data. Maybe something's going wrong, you want to tweak or something like that. Also, if your transit's early and you see the egress and you get some good baseline, you can end the night early as well. Of course, there's an image display, or in our case, an image stack display. You can zoom and pan with the mouse, as would be expected, adjust contrast with the histogram at the bottom. You can scroll back and forth through the stack using this scroll bar. So you see the first image in your sequence here, scroll over here, and you see the last image in your sequence. There is a photometer at the mouse location with the photometric value showing up here. So if you want to make a quick photometric measurement, you just point at the star that you want to measure. We have the typical X, Y, and east and north direction arrows, assuming there's a WCS solution for the east and north arrows, and the plate scale. And it gives access to all the AIJ settings and tools. Along the top, there are the most used items in these icons, and then you've got all the settings and functions up here in these menus. The multi-aperture, the differential photometry has a setup panel, and here you select the shape of the aperture you want to use. We currently support circular, elliptical, and pixel based, so an arbitrary shape based on pixels. That's not so much useful from the ground, but it is useful for space-based photometry. You can select directly your aperture size, or there are various modes where the aperture size can be selected automatically. You can select to place brand new apertures or use apertures that you may have saved from a previous run. You can select the aperture tracking mode. For instance, if you're tracking a moving object, you would want to check that box. And you can set up auto comparison star mode. So if you have auto comparison stars enabled, you set up the range of stars and the number of comparison stars that you want to find. And AIJ will go place apertures on those automatically so that you don't have to do it by hand. There are various options down at the bottom for what shows up while photometry is running. The more you add, the slower it gets, but it's quite useful for troubleshooting sometimes to turn those on to see what could be going wrong. With like if your images jump and if your images are not plate solved, the apertures may not follow the jump of the field in your images. If you have WCS solutions, it will follow it anyway. And once you click place apertures down here at the bottom, you'll be interacting inside the image window again, and you'll just click on stars where you want to place an aperture. Typically, you'll only click on the target star, and if you use ARIAN-DEC to locate apertures, it will do that for you as well. So basically, in that case, if you use RNDEC and AutoCompStars, all your apertures will be automatically placed. You just press enter to start your photometry run. When photometry finishes, you will have a measurements table that's displayed. This contains all the photometric data. Each row in the table contains all the photometric data for a single image. So this is image 1 through the last image in your stack down at the bottom. And the table is interactive with if you have the data plotted. So if you move the mouse around in the plot, it will highlight the row that corresponds to the data point you're hovering over in the plot. It's searchable, sortable, and editable now, which can be dangerous. You shouldn't have any reason to need to edit unless you're doing a custom project or something that's not for TFOP SG1. Then the plotting capability has two different major panels. The one is called Multiplot Main. It controls all of the options that are related to the overall plot, such as titling, axis labeling, axis scaling, and the legend, as well as plot size. But now you can also drag the plot window itself and change the size too. The second window is called Multiplot Y Data. In this window, each row across corresponds to a data set that you're plotting in the light curve. So this first row, which is marked with blue here, corresponds to these blue dots at the top. So it's set up, the blue light curve is being displayed according to the settings across this row. The green light curve you can see is on row 3 here. You don't have to enable every row. That's done with these check boxes. But this is the actual detrended, fitted, and modeled light curve version down here. And then at the bottom, you will see a variety of systematics indicators that we like to have plotted. It helps us in reviewing your data. You can also, of course, set the symbol and shape and things like that. The fitting mode, which will make a fitting window pop up that I'll show next. And then there's data averaging and then data binning in the output. Let's talk about the plot window next before we go to fitting. Again, it displays all of the data sets that you want to show. It's interactive with the mouse and table, as I mentioned before. You can zoom and pan around in the plot if you need to. That's often needed for test data, those very long test sequences. And this is the light curve fitting panel itself. So you would just go in here and set up the initial settings. Usually the defaults will work for a deep transit, but if you're following up a shallow test transit, you may want to custom set some of those to what the test values are to help AIJ find the transit. You can view the fitted values. That's this row of our column of numbers here. And you can manually select detrending parameters here. And when you change those, you'll see the light curve update in real time. Our automation of optimization capability is in this section down here. You can automatically remove bad data points. We have 3 different algorithms that you can use, like 3 sigma removal of data points. So you can clean your light curve, just don't over clean it. You can automatically optimize comparison stars. Once you run these things, you'll see your light curve update, and the same for detrending. That's done here. You just click start. It'll select the best detrending parameters. We provide a reference star panel, and you get a checkbox for each aperture that was placed in the photometry run. And you can take reference stars in and out of the ensemble, the comparison ensemble, by deselecting it here. When you do that, you will see the light curve update. So you can flip through these and see if you have one bad actor. The optimization will do that as well automatically, but if you want to play around, you can do it by hand by going into this panel. And then finally, or no, this is next to last, we have a add astronomical data panel. If you didn't use, you can use your own calibration software and still use Astrométier to do the photometry. So if you still need to add BJD, you can do that as part of the photometry run. Just set it up here. It can be set up to run automatically by enabling this auto checkbox, and it will run automatically at the end of every multi-aperture run. And then finally, our last screen is the coordinate converter panel. And this is where we can convert between, for instance, your date time in your header to BJD TDB. That's what this software does. We have a user interface to it, but mostly it's controlled automatically by the other features that we've already talked about. And it also calculates observability parameters, air mass, and the direction your telescope would have been pointed at the time indicated, and the location of your telescope. It also handles leap second calculations for the BJD TDB calculations. And as I mentioned, it can be manually controlled, or most of the other codes automatically control it for you. So then all you need to do is submit your results. To do that, we have a file save all capability. So with one action, you can save all the files that we need for SU1 data review and for upload to ExoFOP. The only thing you need to do after that is run the NEB check from the measurements table that gets saved. And then you upload the results of all of that to ExoFOP and send me a summary email so that that'll trigger me to go review your data and record it on the TTF. You can then go select and observe your next target, hopefully. I will take you quickly through some publication stuff. First, the techniques that are typically used for transiting planet discoveries by TFOP members. The first is statistical validation. This is done using only photometry for the most part. Can be TESS and or ground-based light curves. The goal is the goal of statistical validation is to show that there's less than a 1% chance of a false positive. In other words, that you're 99% sure that it's a planet, but you're not you can't get to 100 with photometry alone. Sometimes it can use other ground-based data to help strengthen the result, but still we only get a planet size, not a mass. The approach that we really want to always have, if practical, is the radial velocity mass confirmation approach. That uses both the transit data and the radial velocity data, and we model them all together along with Gaia data and other catalog data. This pushes the chance of a false positive down to essentially zero. And we get both the planet size and the mass, of course, since we have both of these data sets, and thus a bulk density and constraints on the composition. Finally, there's the transit timing variation method. So if you expect a transit to happen regularly at a certain periodic interval, and that time is moving back and forth, that means there's another object in the system tugging on the planet that you're observing. So those transit times can be modeled if we have enough transits from TESS and or from the ground. And if we get enough of those measurements, sometimes we can extract a mass from the TTV information. And of course, we still get the planet size because we're modeling transit data. And sometimes this can also push closer to a 0% false positive possibility. And this is the last slide. I want to quickly take you through the publication process. The way it works is TFOP lead authors. Anyone can propose to be a lead author. Generally, it's a graduate student or professional astronomers. I know there are citizen scientists that have published planet or / brown dwarf papers before. So it depends on what your motivation is and how much you're willing to take on. But these folks will request to me and Dave Latham to post an abstract of the planet that they want to publish, and to post it on a protected website that I refer to as the TESS Wiki or TESS Publications Wiki. This lets lead authors see what other lead authors are doing, other TFOP lead authors are doing, so that people will know if they're duplicating effort or not. Now, they're not supposed to glean data if they're, that's what the publication policy is for. Everybody respects what everybody else is doing. And once they post their abstract, the lead author will review and select data from ExoFOP. That's why it's important that we upload our data to ExoFOP, not just send it to me. I will try to shadow what the lead authors are doing and make sure that they're including the data that they should be including. When I have time, I'm usually able to do this. Sometimes I'll miss one. But you may be asked to provide a short write-up that describes your equipment and the observation that's being published. And I will also try to help with this when I have time as well. And when your data are useful for a publication, you'll be nominated to join the paper as a co-author. And you will need to review the paper and agree to the techniques and the information in the paper, and that you agree to join the paper as a co-author. The lead author then takes care of the rest, takes the paper through the peer review process, and eventually the paper will appear in a peer-reviewed journal, and including you as a co-author. So, oh no, I got one more slide. If you do want to join the fun, if you're new to transit observing, there are a couple of resources that I highly recommend. You'll keep seeing Dennis Conti's name here. He's the leader in this area, and he has a website and a guide called A Practical Guide to Exoplanet Observing that you should work through. He also hosts sample data files, images, and calibration files that you can use to load into AstroImageJ and follow his guide step by step. He also tells you how to set up your telescope in a proper way to do transit observing as well. And y'all probably know more about this than me, but I highly recommend attending an AAVSO Introduction to Exoplanet Observing course, assuming those are still being held. And then I've seen a more advanced course called Advanced Use of AstroImageJ for Exoplanet Observing. I've not been completely through those courses myself, but I do know that people who come out of those courses pretty much hit the ground running and are productive quickly for TFOP SG1 work. Once you feel comfortable, you'll need to apply to join TFOP. Again, we have two ways you can do that. Dennis has offered since TESS launched to be a liaison between SG1 and the AAVSO, and he will work with AAVSO members and qualify them as TFOP SG1 members and recommend you to be a TFOP member. To me, so far, I've agreed with everyone he's recommended. I don't think anyone's been rejected. And so that's one approach. If you are already an experienced transit observer, you may opt to apply directly following the instructions at the website you see there. That is basically entails sending me an email that answers 4 or 5 bulleted questions there. And some key ones are you have to read and agree to abide by the TFOP working group charter. Every TFOP member does. This is why we can work together fairly. And also read and agree to abide by the TFOP working group publication policy. Okay, that's it. Now let's try to answer some questions.
Thank you, Dr. Collins. We've got a good handful of questions, and we will try to get through as many as time permits right now. So the first question for you was, how does the low spatial resolution of TESS cameras influence the identification and correlation of false positive signals in TFOP? And what observational strategies and photomic techniques do citizen astronomers need to apply to disentangle blended stellar signals within the TESS point spread function?
Well, so your ground-based telescope, you're going to generally just automatically, if you're focused, you're going to generally have much higher resolution than TESS will have. TESS will have higher photometric precision, but spatial resolution will be generally higher from the ground. So that will just normally fall out. If you have 2 stars that are blended together in your data, then it's still tough to separate those. And that can happen. We have some very crowded fields.
Okay, great. The next one, to what extent can the integration of AI into AstroImage enhance the processing and analysis of TESS TFOP science subframes, thereby improving the efficiency and accuracy of exoplanet candidate validation?
Uh, I don't know because I am not an AI expert. I try to use AI. I tried to use AI to build this presentation, but it didn't help me very much, unfortunately. So I think that depends on the expertise that does the AI building work, and I don't know. Pablo, if you would like to build us an AI module to try out an AIJ, we will gladly work with you. Our code is open source and you can work with us on GitHub with it. But unfortunately, we don't have AI expertise on the development team.
Okay, next question is, does citizen science projects on the Zooniverse platform really help find the exoplanets? This person's been doing Planet Hunt and TESS and Planet Hunter in GTS for quite some time.
Yes, they find planet candidates, right? But you need all of the observations that I went through to confirm that they're either a planet or a false positive. Now, I'm not aware of Planet Hunter in GTS. I guess that's using NGTS data that's hosted like the test data are in Planet Hunters. But you still need to do, if you want to confirm the planet to basically a 0% false positive certainty, then you need radial velocity data. So you still need TFOP-like work to confirm those planets. So we take in a lot of planet candidates from planet hunters. They're entered as CTOIs on ExoFOP, and those will eventually end up on our list, and we will follow them up.
Great. Are any of the SGs leveraging machine learning, deep learning models to help cover so much analysis of so many TOIs?
Not that I'm aware of.
Okay.
Follow-up is done by so many different instruments that you would probably need to train the AI on each individual instrument. So I don't know. Now, AI applied to test data, that's a different story that has been done. There's a paper out on that. But you have a large training database, and you have a large set of TOIs that you can train the AI to know what's a false positive and what's a planet candidate.
How does one confidently determine the true source of the transit event when multiple stars are present within the TESS pixel scale, especially for crowded fields or faint targets?
Well, if you can't separate it from the ground, then it's still difficult. Eventually, someday, Gaia may be able to do it when Gaia collects more and more data points. Gaia has a resolution of like an arc second. And Gaia can detect in some unpublished data that we get some results from, submitted to SG1. They can pinpoint the source of a TOI signal. But generally it's for short period and close-in planets, giant planets.
Dr. Collins, I'll let you read this next one from Jack Stone, please.
Okay. B band equal or approximately blue filter, CXB exoplanet filter. The exoplanet filter, the CXB, is a different abbreviation than I've seen before. I think I've seen a EXO, exoplanet filter, exo filter, but those are different things. The exo filters generally include the center of the optical band, like R band and I band, and maybe out to Z band, but they just cut off the blue. I don't know what CXB is, though. If CXB is an exoplanet blue filter, then yeah, that should work okay.
Okay. What is the follow-on process when an observation goes from PC to VPC plus?
Yeah, so that can get complicated. Ideally, we want to see and confirm the transit signal on the target star using ground-based photometry, using an aperture that excludes all other Gaia stars that are known, because Gaia is going to resolve stars down to 1 arc second and down to like 20th magnitude, fainter than we need to work generally. So if we can exclude the known location of all known Gaia stars that are bright enough to cause the TESS detection, then it will get promoted to what we call a VPC, or verified planet candidate on target. Now that's different than validated planet candidate. So I just call them verified on target. Beyond that, when we do the chromaticity check, that's when we'll need a B band check. If we have consistent depths in both a red band or an IR band and a blue band, then it will get promoted to a VPC. If the ephemeris is coming back consistent for all of our observations, we will then disable that TOI for further observations. If the ephemeris continues to jump around, then we may continue to observe it to see if we're finding TTVs.
Great. How can you join the SG1 if you are starting out?
I'm looking at the timestamp on that one, 2:30. So I think that was asked probably before that last slide. If there are more questions beyond that last slide, maybe put a new question.
Okay, great. I'm going to keep going. Actually, Dr. Collins, if you can pop it back to that last slide, that way, I think a few of the questions in here are going to be about joining. That way people can refer to it. We will go ahead and not answer those live, folks. So if you had a question about joining, it will be on the slide that will be on the screen.
Okay, there you go.
Okay, which is the minimum mirror aperture required and the camera and equipment recommended for this program?
There are actually no minimums specified. Some people use the, I'm forgetting the name of them, the SETI telescopes that were done in collaboration with SETI. They're quite small. Now, they can usually only do hot Jupiter type stuff. It just depends on what you're willing to work on. If you're willing to work on hot Jupiters, you can get away with a smaller telescope. Most people do the best work with a 14-inch or larger. You can contribute plenty of work if you have a kind of a 12 to 14-inch or larger telescope. Equipment, CMOS cameras these days tend to do fine. I don't know the current model numbers or anything, but some people have also contributed results from DLSR cameras, color cameras, and AIJ does have a mode where you can separate the pixels, the red, green, and blue pixels, into 3 different light curves. And actually produce the color data from one observation. But again, those are best for deep events around bright stars. And most of that cherry picking has been done, but it's not to say that all of it's been done.
Great, thank you. Dr. Collins, I'll let you take the next one, please.
How do we determine if our data meet the -1? Well, so this is something you need to get a feel for. So AIJ has binning, and you can just set the binning up for 10-minute bins. And then you look at the RMS value, and if it's roughly 1 ppt in the 10-minute bins, which is provided in the legend, then you will know that your equipment is producing that. So I don't think you can determine it ahead of time. It's a feel you need to get for your instrumentation in general. And then once you get that feel for the brightness of the star that you need and the number of comparison stars that you need to reach that precision, you will have a good idea from the start. I think most citizen scientist telescopes can do 1 ppt per 10-minute bins, as long as tracking is pretty good and the star is reasonably bright. V equals 12 or brighter, maybe. Now, if you've got a 6-inch telescope, maybe not, but kind of a 12, 14-inch telescope or bigger, I think you can generally do that.
Okay. And that answered this next question too, correct? Just check me real quick. I think it did.
Yeah, it doesn't directly give the appropriate minimum telescope aperture, but it does give that recommended noise ratio.
Okay, great. Next question. Is there a way to filter out output from the TESS transit finder to identify transit where observations by small telescopes can be accomplished? It seems that most of those listed require larger professional telescopes, i.e. chromatic.
Yeah, sure. There is a box where you can put transit depth, a minimum transit depth. So maybe go in there and put 5 PPT or 5 millimags, and then you can filter out all the shallower ones.
Okay, great. I don't think the next one is quite a question. Next question is, are all the tools web-based, local on your computer, or both? If local, what operating systems are supported?
Sorry, I was distracted reading the other. Are all the tools web-based, local on your computer? All the tools are web-based except AIJ is installed on your computer. But we have installation packages that install on Linux, Windows, and Mac.
Okay.
And that's because the data movement required is large to do the photometry. more difficult to shuffle all of your images across the internet to do photometry on a server somewhere.
I will let you take the next question.
Okay, can you explain how targets get assigned to SG3 and where those are tracked? Those are tracked, David Giardi handles that. They do not get assigned to anyone. They have their own priority system that's used that I don't know the details about, but it tells them what type of observation is needed. And when someone has a high resolution imaging run, they tend to get like a night of data. So they'll just go observe all the, it's not like SG1 where you have to wait on a transit. They can observe any star that's up. It's not ephemera space. So they just choose their own targets and observe what they want, as far as I know. And we know previously, okay, I didn't know if there was something below that. So this observation can be done also with C-Star S50. I don't know the telescope names or if does 50 mean half meter or does, I'm not sure. I don't know citizen telescope or off-the-shelf telescope manufacturers well enough to answer that. I would say yes for deeper transits of brighter stars. Okay, this may be a question outside the scope of the presentation, but in period analysis, what is the false alarm probability and what does it represent statistically when searching for additional periodicities and well, okay, so this is not really SG1 related. This is when you're searching a periodogram for what might be the source of a transit signal. There will also be provided a false alarm probability for each particular signal that's in the plot. So you'll have two plots, right? And or two signals usually plotted on the same plot. And there are different ways of doing the false alarm probability. I'm not an expert in the area, but I think it has to do with just trying a bunch of different assumptions. And with a lot of assumptions tried, then you can assess some false alarm probability. But how does it detect the chosen? How does it check affect the reliability? Well, certainly, if you're close to the false alarm probability, you're less reliable that the signal is what you think it might be. But I don't know how to put numbers on that. I'm sorry, I can't really get any closer on that. Good evening. Wish to find out why different flux formats exist on test data and these cannot be standardized. Well, that's beyond me, but for instance, SAP flux and PDS flux, the SAP flux is the undetrended aperture photometry, and the PDS flux is the detrended photometry. So you want both of those. Sometimes you don't trust the detrending done by spot. I'm not aware of what the other two are, depth flux and KSP flux. But there are different pipelines. I mean, the pipeline of record is the Spock pipeline. MIT also runs the QLP pipeline. They're the two primary pipelines, but as the person notes, there's light curve. You can produce light curves from the light curve tool with a K. There are various other tools. So yeah, I don't know. That's beyond me. I would say if the units of measure differ, that's the last question. You just need to normalize and not worry about what the units of measure are. normalize the data to the out of transit signal. Okay, is the field of view tool you demonstrated publicly accessible? Yes, it is. You can go to ExoFOP, the specific tick page on ExoFOP, and there's a link at the top. I see J2000 for Epoch. Is there a way to have it use J now? I'm not sure exactly where that is referring to. There are parts of AIJ that do J now, as in the date of your observation. So I'm not sure how to answer that one. I'm sorry. I would have to know more detail. Does TFOP offer any training or support with AIJ? We do not directly, because we are 2.5 people right now. So we just don't have the resources. I do support AIJ through the AstroImageJ user forum, which is public. You can post questions on there. I will answer them as soon as I can. I don't have any specific training programs. I'm in the process of hopefully hiring a postdoc soon to help out. And if that's the case, we will have some bandwidth and I can put together some courses. However, the AAVSO courses are quite good. So unless the timing is just bad, I would certainly recommend starting there. There are various tutorials out there, including Dennis's, that I referenced in the talk. That's on the screen right there, A Practical Guide to Exoplanet. Is there a tutorial and vetting process? I don't know the vetting process. Well, do you mean maybe vetting as in accepting? Dennis can tell you what he looks for. I look for, if a citizen scientist is applying, I want to see 3 or 4 light curves that you've observed with your own equipment, and that you have reduced yourself and created the plots and so forth that we need for SG1 work. That's pretty much it. So if you can observe and create the light curves, that's pretty much it. And you're willing to agree to abide by all of our policies and not disclose any of our proprietary data to non-TFOP members. We're pretty open. Why would a transit be seen in one filter and not another? So if the orbiting object is another star, a transit being the same depth in all different filters depends on the orbiting object being dark. In other words, not contributing any light itself. When you have a star orbiting another star, both stars are putting out light. So the transit depth, when one star transits in front of the other star or eclipses it, if the star colors are different, and they almost always are, then the transit depths will be different in different filters, because a different fraction of the colored light is being obscured when a star crosses.
I think the next one is kind of more for the AAVSO. We will be sending the presentation out. It will be on YouTube within the next couple of weeks. We will also try to put relevant links underneath it. And
Okay.
Dr. Collins wants to share anything, she's welcome to, for us to put it in the captions of the YouTube at the bottom, underneath in the description. But otherwise, just look for this presentation to be up in a couple weeks.
Okay. Would the transit time vary with the time of year as the result of the change in distance to the Earth? The answer is no, and this is why we use BJD-TDB. BJD-TDB corrects for all the changes throughout the year. Otherwise, we can get a plus or minus 8-minute variation just depending on the Earth's orbit and other things. So that's why we require BJD TDB time format. Or if our early indicators light was instantaneous changes in gallium. Yeah, so I think that's good on that one. Would students involved in TFOP be allowed to present their data? Yes, the answer is yes. If you observe data, it's your data. You can also post it on TFOP publicly. However, what you have to be careful is if we have private TFOP information, like if we found that there are TTVs in the system, or if the ephemeris is significantly different than what's published, we may not want to give that part of the information away, so that it could compromise a paper that is being prepared for publication. But in general, yes, you can show your own data. And many students have done that.
Real quick, Dr. Collins, just for the sake of time, anybody who asks questions after like this next minute or so, we're going to go ahead and cut questions off so that we can be respectful of everyone's time here, but we do want to get to a few more of these questions.
Yeah. Okay. If you don't have photometric filter sets, is an exoplanet filter okay? It's okay if we're asking for the first light curve observation. If we're asking for a blue band filter, then it's not okay. So if we're asking for a red band filter, it's okay. Okay, had a brief power outage here, some may have missed it, but is there priority for the target objects? Yes, there is a priority column on the TTF output, which comes from the SG1 TOI list. The priorities are only 1, 2, and 3. You have to make your own choices, but those can help guide you. Generally, the priority ones, though, are small planets, so they may be tough to do with citizen scientist telescopes. So you may often be observing priority 3s. Beyond that, no, just pick what I would say if you have a full transit observable and 4 partial transits, go for the full transit. If you have 3 full transits observable, go for the one that you have a field of view that you'll have the best comparison stars in, that you would end up getting the best photometric precision for. Okay, my transit data generally do not meet statistical quality because of atmospheric turbulence in New England. Does anyone use an adaptive optics? I don't think that is going to help much. There are people who contribute from the New England area, and it just depends. Make sure you're talking about your bend data quality, and try to get your telescope to guide as precisely as you can. And you may have to observe brighter stars if your telescope aperture is smaller. I'm not sure here, but atmospheric seeing, I did most of my PhD thesis from an observatory here quite close to Louisville, Kentucky. And did it add some noise in the background? Yeah, but from the sky background, but it didn't prevent me from doing Kelt data work, follow-up work. I don't know if you know Paul Binney, but he is a frequent SG1 observer, and I believe he's in the New England area, Dennis Conti as well. Okay, any scope for SG1 membership for those without access to their own telescope? But with experience in reducing data with through the NASA Explain Watch. So you can apply for telescope time through LCOGT. as an educational grant of telescope time. I don't know the details about that, but you can see it on their website. I don't know if there are other such opportunities, but I would turn to LCOGT first, plus the fact that their telescopes all work quite well. So. Okay, how does TESS follow-up observing program balance the need for high precision photometry and spectroscopy and exoplanet confirmation with the heterogeneous data quality provided by citizen astronomers? Well, so balance between high precision photometry and spectroscopy. So we don't really have to balance the spectroscopic side relative to SG1. I don't think there are really folks contributing to recon spectroscopy from the citizen side. But from the photometric side, that's what I do. I judge the quality of your data. If you have a 10 ppt transit depth detection and a timing extracted from that, even if your photometric scatter is high, as long as it's a smooth scatter, the values that we extract for it should be fine. It's just when you have large systematics that cause the scatter to be very uneven in the light curve. That's where things become suspicious. Calibration, machine learning, overcome. We already talked that. I don't know the machine learning. I'll just say the quality of the data starts with the observation. So learn Dennis Conti's skills from his practical guide and follow those. The number one is do the best you can to make your telescope track and guide to the same pixel throughout the night. I know it's difficult, but I know we have a lot of citizen observers that do it. Okay, next. I'm a master student. Germany would like to get involved in research related to that example. Perhaps leading to a master's degree involved. Well, for students, students really need an advisor at their local university or college that can lead them. Again, we just don't have the resources to be the academic advisors for students. So you need someone that can lead you on it. You can make proposals, like I mentioned earlier, to LCOGT to try to get time on a telescope. And then it's kind of between you and your local advisor as to what would qualify you for your own program. If you don't have a local advisor, I'm not sure what to suggest at that point. I mean, maybe you can find an advisor at another school or something. If you can show them your dedication to the work that you want to do, and things that you've learned on your own, things like that might help you be able to track down an advisor. It's not my area of expertise either, because I'm more of a data scientist rather than an instructor. Okay, what size scope and filters are typically used? Like I said, 12-inch and larger typically. Is what I see. I've seen some 6 inches, but I think 12 and above tends to be the right sweet spot. Has the program experienced any federal funding issues? We certainly have uncertainty in our funding right now, as every federal employee does. We are the Smithsonian Institute. I'm sure you've seen us in the news in the past few days. But as of now, if the president's budget continues as was proposed, then we are in the budget. But in the current day, we never know what's going to happen tomorrow. So yeah, uncertainty. Are accepted also observations where they're capture only ingress or egress? It depends. And I will specify that in the comments back to observers that show up in the TTF comments. So it will either say a full transit or an ingress or egress. Almost always a full transit is observed, but some transits from TESS are hours long and it's impossible to observe a full transit from the ground. So those will specify an ingress or egress. And many times you're intending to get a full and clouds move in and you get an ingress only. Yeah, you can still submit it and I'll decide if it's useful or not. So yeah. We're going to find information on using AstroImage-J for doing photometry of test data. Dennis's guide, the one that's listed right here, I think is the best way to get started. It has step-by-step instructions on how to use AstroImage-J from a practical perspective for transit observing. I can recommend a quality review that citizen scientists should perform to determine whether to upload an observation. Well, yeah, that's tough to say. I mean, if you expected a transit, you would want to kind of, if you know what a transit looks like, I showed a couple earlier in the presentation. If you see the dip, the characteristic transit shape, then your data are probably good enough. But if your data are maybe transit and then skew way off up or down or something, unless there's a reason for that and it can be detrended out, then that may make the data not useful. So, and also there are a lot of observations where a transit is ruled out. If you have a 10 PPT transit and you can look at your data and you can see that there's no scatter beyond 2 or 3 PPT, then there cannot be a 10 pp transit in that data, and those data are useful. We can then try different orbital periods to try to track down the transit. Will your data be around in 100 years? Well, that depends on a lot of things that are not in my control. That is the point of ExoFOP. As long as NASA funds it, as long as NASA keeps the data around, yes, they will be there. Will all the improvements you have made, how many candidates make it through the SG1 and SG2 filtering to SG3 now? Well, a lot of these are kind of done in parallel, but there's roughly a 30 to 40% false positive rate for TOIs. If it's giant planets, the false positive rate is closer to 40%. For small planets, for Earth radii and smaller, it tends to be closer to 30%. What is a PPT? That's a good question. You can quickly just think of it as a millimagnitude. PPT stands for parts per thousand, but it's very close to a millimagnitude unless it's a very large millimagnitude and then they start to diverge. But a 10 PPT signal is very close to a 10 millimag depth, but it means parts per thousand, but you're not having to deal with magnitudes, and all the modeling tools strip all magnitudes out. We're working on relative flux, normalized relative flux with no magnitude. So we speak in terms of relative flux, and that's the PPT number. What about data from exoplanet filters? Yes, that's fine for our red band requests. if it's the CBB exoplanet filter. And I have found long periods in one intermediate polar system using test data, but the period peaks show Gaussian shape spread in power spectrum. How can I verify whether the period is real? I don't know. I think that's kind of outside the scope of this talk, but I don't understand what tools you're using, and I don't understand your knowledge baseline. So there can be a lot of answers there depending on those things, but this could lead to a 20 or 30-minute discussion. So with time constraints, I think we should move beyond that one.
All right, Dr. Collins, you have really gone above and beyond. Thank you for your presentation, for your time today, for answering everyone's questions. I know we all very much appreciated it.
I enjoyed it, and thanks for the invite.
Thank you. So I'd also like to thank this webinar sponsor. Boise Astro has sponsored our entire 2025 webinar series. Boise Astro provides online astronomy education, observatory research resources, and research experiences to students and schools to perform observations, conduct research, and publish results. I also know Boise Astro is here today and was making some wonderful, helpful comments in the chat for those of you who are interested. Please check out their website at boiseastro.org to learn more. Also, if you enjoyed today's webinar, please consider a donation by scanning the QR code on your screen or going to aavso.org. All donations are tax deductible and enable us to offer educational opportunities like this one free of charge. Next up, our 114th annual meeting is coming up November 1st and 2nd in Portland, Oregon. We would absolutely love to see you there. You can find out more information by going to aavso.org/114 or scanning the QR code on your screen, and you can see who our keynote speakers are going to be. Again, we would love to see you there. So lastly, just thank you all so much for being here today. Thank you for your time, your interest, and your dedication to what the AAVSO does. And we look forward to seeing you next time. And thank you again, Dr. Collins.
Thank you all.